I'm Patty Simpson with Simpson Math. In this video, we're going to graph this polynomial completely. So the first step we perform when we are graphing a polynomial is we do the end behavior. We can look at the equation to find out what's happening on the ends. We look first for that leading coefficient, and that leading coefficient is 2. Since the 2 is positive, we know that this polynomial is going to rise on the right. Next, we look at the degree of the polynomial. The degree of this polynomial is 3. That 3 is odd, so we know that it's going to have opposite end behavior. And it's going to, on the left then, since it was rising on the right, it will fall on the left. Then, because the degree of the polynomial is 3, we know that there are going to be one less turn, so there's going to be 2 turns. And that degree of the polynomial also tells us there are 3 roots. So we get a lot of information just by looking at the polynomial. We know that it's going to look something like this: rise on the right, fall on the left with 2 terms. Then we're going to look for the y-intercept. And we know that when we are looking for the y-intercept, that on that y-axis where it intersects, our x is always equal to 0. So we are just going to substitute in 0 everywhere we see an x. So I have 2 times x cubed plus 3 times 0 squared minus 8 times 0 plus 3. That equals 0, this equals 0, that equals 0, and it leaves me with 3. So I know that I have a y-intercept of 0, 3. Now, we've done all this in the past in previous videos. In this video, we're really going to be looking at the challenges of the x-intercept. But we start off the same as we did in the past, where we know that the x-intercept, again, where the polynomial crosses that x-axis, we know that our y value now is equal to 0. So I'm just going to substitute in 0 for y, so that I am now trying to factor this polynomial. I'm just going to go through and find the factors of that polynomial. And as I factor it, I say, well, first thing I look for is the greatest common factor. There's not one in this polynomial. So there are 4 terms, so I'm going to group it. I'm going to look at the first 2 and factor out the greatest common factor, which is x squared. Leaves me with 2x plus 3. Then I'm going to factor out the greatest common factor of the last 2, which the only common factor they have is 1. And that does change the sign in there. But then we look and we go, oh no, these 2 don't match. When we factored with grouping in the past, those 2 have matched. That tells me that grouping does not work for factoring this. And instead, we're going to have to use synthetic division to help us to find a factor that evenly divides into this polynomial. To help us to decide what we're going to divide by with that synthetic division, I'm going to look at my possible rational roots theorem. And remember that the possible rational roots theorem says that we take the factors of the constant, in this case, our 3, and we put them over the factors of our leading coefficient, in this case 2. So we're going to take those factors of one another and find all the possibilities. So first, the factors of 3 are 1 and 3. And we look at the positives and the negatives of those. Then we put those over the factors of our leading coefficient. Here in this case, it's 1 times 2 gives me 2. And those are the only factors. Now I look for all those possibilities. So the possibilities are 1 divided by 1, 1 divided by 2, 1 divided by a negative 1, and 1 divided by a negative 2, 3 divided by 1, 3 divided by 2, 3 divided by a negative 1, and 3 divided by a negative 2. When I do these negatives, I end up with the same ones. So we have 1, 2, 3, 4, 5, 6, 7, 8 possible rational roots. There are 8 possible rational roots. We know that from our end behavior that we are only going to have 3 roots. So not all 8 of those are going to work. In fact, this polynomial might only have irrational roots. This just tells me if it has rational roots, what are those possibilities. So now let's just try one or two and see if we can't get this thing factored. Let's begin just at the beginning of the list, and we're going to divide by this 1. Now, when I use my synthetic division, I'm just dividing by 1. But if I'm writing this as linear factors, that 1 is really the binomial I'm really dividing by, this binomial of x minus 1. Remember, the sign changes. So now I'm going to divide by this 1, and I'm going to use my coefficients here, 2, 3, -8, and 3. I'm going to do that with to use synthetic division. So I'm using the synthetic division. Drop down that 2. 2 times 1 is 2. Add, you get 5. 1 times 5 is 5. Subtract, you get -3. 1 times a -3 is a -3. And add that, and you get 0. So it turns out that when you have no remainder, such as this, that this actually is a factor. This is going to be a root. We got lucky. On the very first try, we found one of the roots. So we have partly factored this. We know that this polynomial factors to, well, the binomial that we had there. So we have 0, 0 equals, I'm just rewriting this polynomial as factors, x minus 1 times, remember this quotient is my other factor. So I have 2x, bring it down 1 degree from 3 down to 2, plus 5x minus 3. So I have partially factored this, but I don't have linear terms here. So since I don't have linear terms, I need to keep factoring. I could use this and continue to work through my list to see if I could find another rational root. Or in this case, it's 3 terms. Maybe my AC method will work. So we're going to go through and find those factors. So I have x minus 1 times 2x squared plus 5x minus 3. And it turns out that AC will work with this. My A is 2, my C is -3, so my AC is a -6. The factors of -6 that add to be 5 are a +6 and a -1. That multiplies to be -6 but adds to be 5. I rewrite this term using those factors of -6, and then I group so that in that first grouping I'm taking out a 2x, leaves me with x plus 3. In this last one, I'm taking out a -1, leaves me with x plus 3. I go, oh, thank goodness, they match. Because when they match, that lets me know that I can continue factoring, so that this is x plus 3 comes out of both of those and leaves me with 2x minus 1. That whole time, this was being multiplied by that x minus 1 the entire way down, if I want to keep this so that it's equal to the step above it. And the whole time we had it set equal to 0. So just making sure that each line is equal to the one before it. I have now factored that polynomial down to its linear factors. And now we set each one of those factors equal to 0 and solve them. And we will find those x-intercepts, or our roots. So here I have x equals 1. X equals a -3, add 1, divide by 2, and you get 1/2. So it turns out that our roots here were at 1, -3, and 1/2. If we had tried any of those 3, they would have evenly gone into our polynomial. If we had tried -1, -1/2, 3, 3/2, or -3/2, they would not have evenly gone in. So you see, this gives us our possible rational roots. But it doesn't mean that all of them work. In fact, none of them could work because we could have irrational roots. So my x-intercepts here are at 1, 0, -3, 0, and at 1/2, 0. We talk about the multiplicity. In each case here, it only shows up one time. So the multiplicity of each one of those x-intercepts is just 1. What we care about that multiplicity is that it is odd. So that tells me that it's going to turn at each point. So now that we've found all our pieces, we know what is going to happen on the ends, we know our y-intercept, we know our x-intercept, we are now ready to graph this function. I didn't leave myself much room to graph the function, but let's see if we can give a graph here. So I know that my y-intercept is at 0, 3, 1, 2, 3. I know that my x-intercepts are at 1, 0, negative 3, 0, and 1/2, 0. I know that on the right it's going to rise. I know that on the left it's going to fall. I know that it's going to cross at each one of these points, so it's going to come up some point or another, turn around. We'll learn that turning point in calculus, although I might get more specific by substituting in -1, -2. Then it's got to turn back around, come through that x-intercept, and I know it's going to cross through there because not turn at each point, it's going to cross at each point, Ms. Simpson. This is going to cross at each point. When the multiplicity is odd, it crosses at each point. Sorry about that. So it crosses at this point, it crosses at this point, and then it turns around somewhere and comes back up and crosses at that last point. So there's our polynomial graphed fully and completely. And notice how we can use that possible rational roots theorem to help us to factor. I'm going to graph another example in the next video where we have a double root that we have to look for. Math Made Simple is Simpson Math. Thanks for watching.